Hello to all, welcome to the channel Money's Gate Tech Vision. In this lecture, I am going to solve GATE 2025 problems from the topic Control Systems. For that, I have taken the GATE Electrical paper and Electronics paper. The topics which I have taken is common for Electrical, Electronics and Instrumentation branches. So all those branch candidates can watch these solutions. So let me move to the presentation and let me solve the problems one by one. So this problem is taken from the topic Routh Hurwitz Criterion. First, let me read out the problem. Consider the polynomial, one higher degree polynomial is given. Let L, I or be defined as follows, where L is the number of roots with negative real parts and I is the number of roots that are purely imaginary. R is the number of roots with positive real parts. Which one of the following options is correct? So negative real parts means the roots which are lying in the left half of S-plane. And purely imaginary means the roots which are lying on the imaginary axis itself. Positive real parts means the roots which are lying on the right half of S-plane. So let me apply the Routh array and we can find the location of roots. So directly characteristic polynomial is given. So we can apply the Routh array directly. So let me form the Routh array. S power 5. The S power 5 row elements are 1, alternate coefficient is 3, the coefficient of S cube, and 2, which is the coefficient of S. And S power 4 row elements is, the coefficient of S power 4 is 7, and alternate coefficient is minus 33, which is the coefficient of S square, and minus 40 is the constant. So to form the S cube row elements, so we can calculate for that. So 7 into 3 minus 33 by 7. So that is nothing but 54 by 7. So let me calculate 54 by 7. Again, and this one 7 into 2, 14 minus of minus 40, again 54 by 7. Okay. So let me simplify the row elements as 1, 1. The same row elements became 1, 1. And then to form the S square row elements, we have to take the S cube row element and S power 4 row elements. So for the calculation, 1 into 33, 1 into minus 33, and then minus 7. It will become minus 40. It will become minus 40 again. And then for the next calculation, 1 into minus 40 by 1. So minus 40 again. Okay. So this will be simplified as minus 1, minus 1. Okay. For S power 1 row element, we need to take the S square row elements and S cube row elements for the calculation. S square row elements and S cube row elements for the calculation. So for S power 1 row element, minus 1 into 1, minus of minus 1, it will become 0. So S power 1 row element will become 0. 0. So if we get 0, we can form the previous row elements as auxiliary polynomial. So we can form the auxiliary polynomial as minus S square minus 1 equal to 0. So if we differentiate that auxiliary polynomial, it will become minus 2S. So we can replace the S power 1 row by this minus 2. Okay. And then S power 0. So to find out the S power 0 element, we need to take the S power 1 element and S power 2 element, S power 2 row elements. So minus 2 into minus 1, that is 2 by minus 2, again minus 1. Okay. So let me sort out the first column elements. Okay, we need to check number of sign changes to find out the roots which are lying on the right half of S plane. S power 5, S power 4, S power 3, S power square, S square, S power 1, S not. Okay. First S power 5 element is 1. So I am writing only the first column element, then only we can check the number of sign changes, and then 7. Simplified S cube row element is 1. And then S cube first column element and S square first column element is minus 1. S power 1 first column element is minus 2 and S power 0 minus 1. So here check the number of sign changes 1 to minus 1. After that negative only. So only one sign change is there. Only one sign change is there. So we can conclude only one root is lying on the right half of S plane. One root is lying in the right half of S plane. Okay. One sign change. Therefore, one is lying on the right half of S plane. So right half of S plane means it's nothing but positive real parts. Positive real parts. Okay. So from this auxiliary polynomial, we can find out the roots. S square plus 1 equal to 0, S square equal to minus 1, S equal to plus or minus J. So plus or minus J means it is lying on the imaginary axis. Imaginary axis. Two roots are lying on the imaginary axis. One root is lying on the right half of S plane. And then other two roots are lying on the, obviously, other two roots are lying on the left half of S plane. So let me conclude with that. So let me see the notation. L is the number of parts. L is the number of roots with negative real parts. So this is LHP. Okay. LHP. So L equal to 2. And then two roots are lying on the left half S plane. And purely imaginary S equal to plus or minus J. So that is also two roots. Other one root. There is only one sign change. So one sign change means one root will lie on the right half of S plane. So for positive real parts, what is the notation given? R. So R equal to 1. So this is the solution for this problem. So let me check with the options. So option A is L equal to 2, I equal to 2, R equal to 1. So with the option A itself, we got the answer. So we can pick out the option A. Let me move to the next problem. This problem is taken from the topic signal flow graph and block diagram reduction techniques to find the transfer function. Okay. See, observe the options and the problem. One block diagram and let me find the transfer function for this. And then let me check the transfer function with the signal flow graph. Okay. For that, I am going to move the takeoff point. I am going to move the takeoff point before this block. Then only we can reduce easily. Okay, before the block. So if we move the takeoff point before the block, that respective gain should be added. Respective gain should be added. So for that, I am drawing the block diagram. See, after moving the block, this is after moving the takeoff point, the gain should be added. This is G1. And then again, this is G1, G2. And this summing point is parallel block combination plus plus. Output is Y of S and input is R of S. Now this is one negative feedback loop. And again, this is parallel block combination. So eliminating this negative feedback and parallel block combination, the block diagram will be reduced to. So here open loop transfer function is 1, and in the place of feedback element we are having G1. So we can form like 1 by 1 plus G1. And then parallel block combination, we can add the gains G1 plus G2. So finally, the transfer function Y of S by R of S equal to cascading these two gains G1 plus G2 by 1 plus G1. So this is the transfer function. We have to cross verify this transfer function with all the signal flow graph. So first let me check with the option A. Let me check with the option A. Okay. So in that option A, first let me find the forward loops, forward paths. So for what are the forward paths? P1 equal to G1 and P2 equal to G2. Okay. One is G1 path and other one is G2 path. And then L1. Then we find the individual loop gains. L1 is, so one is this loop, other one is this loop. So G1 with -1 feedback and G2 with negative -1 feedback. So L1 equal to minus G1 and L2 equal to minus G2. So from that we can find the delta. Delta is 1 minus sum of loop gains. So 1 minus of minus G1 minus G2 is 1 plus G1 plus G2. So let me find the transfer function. So if you find the transfer function using Mason's gain formula, we are having two paths. So P1 del 1 plus B2 P2 del 2 by delta. So del 1 del 2 equal to 1 because there are no non-touching loops. Okay. For in the first signal flow graph, there is no non-touching loops. So we can conclude delta 1 and delta 2 equal to 1. So P1 only we have to add P1 and P2. So P1 is G1, P2 is G2. So G1 plus G2 by delta is 1 plus G1 plus G2. So let me compare this transfer function with the block diagram reduced transfer function. It is not equal. So option A is not correct. We can conclude the option A is not correct. Okay. So let me check out with the option B. Let me check out with the option B. So if we check with option B, again we can find forward paths. So this is with option A. And let me check with the option B. P1 equal to G1 is one forward path and G2 is another forward path. So if we check with the loop, only one loop is there. That is G1 with -1. Okay. So other loop, see here, other loop, G2 here, backward it's not coming because this one gain is given in forward direction. Okay. So it is not feedback loop. We cannot take G2 and -1 as feedback loop. So we can conclude with only one individual loop is there. So from that we can find the delta. We can find the delta. So delta equal to 1 plus G1. And from that we can find the transfer function. So transfer function again, addition of forward paths is G1 plus G2 by delta is 1 plus G1. So let me compare the transfer function with the block diagram reduced transfer function. It is equal. It is equal. So option B is correct. Let me check out with the other options. Let me check out with the other options. See option C, only +1 is given. It is not negative feedback. So by seeing that itself, we can mark it as wrong. And in option D, see, like the option B, but see here it is G1 and it is G2, and here G2 loop is given. Okay, G2 loop is given. So if G2 loop means delta will become 1 plus G2. So in the place of G1, we will get G2. So that transfer function will not match. Okay, so option D is also wrong. So only option B is correct for this problem. This is the proper signal flow graph for the given block diagram. Let me move to the next problem. This problem is taken from the topic Routh locus. Consider the unity negative feedback system shown in figure where gain k greater than or equal to 0. The Routh locus of the system. Okay. For what values of k will the system in figure have a pole at -1 plus j1? So Routh locus plot is given. We need to find the k value for which the pole is at -1 plus j1. So from the given Routh locus, we can find the transfer function, and from that we need to find for which k value we can get that in complex form. So let me mark out the zeros and poles, and let me mark out the transfer function also. See here, there are 2 zeros and 2 poles. Z1 equal to -3 and Z2 equal to minus 4. These are zeros. Zeros. And then poles P1 equal to minus 1, P2 equal to minus 2. These are poles. Okay. So we know numerator factors are zeros and denominator factors are poles. So we can find the open loop transfer function as k into g of s. So k into zeros are s plus 3. So with the zeros we can form the factors s plus 3 into s plus 4 by poles are s plus 1 into s plus 2. Okay. So we need to select the k value for which you need to get a pole as complex form. Okay. So if we check k equal to 1, k equal to 2 means there will be no change in the poles. Let me check with the options. K equal to 5. In the option A, k equal to 5. So k equal to 5 means there will be no change in the poles. So option A is wrong only. Option A is wrong only. And option B, k equal to 15. That is also wrong. For all positive values, there will be no change in the poles. So for all positive values of k, option D is also wrong. And option C, check with option C for no positive value of k. So it may be, they have given only for no positive value of k. That may be negative or that may be complex form. Maybe if it is complex form, we can get the pole as complex form. So they didn't specify that. So we can mark out the option C as correct. For no positive values of k, we can get the pole as complex form, minus 1 plus j1. Okay. Let me move to the next problem. This problem is taken from the derivative controller. A controller D of S is of the form 1 plus KDS is to be designed for the plant. G of S system function is given. The value of KD that yields a phase margin of 45 degree at the gain crossover frequency of 10 radian per second. Now, so this is controller function D of S and G of S is given. Okay, so both combination is open loop transfer function. So let me mark out that. So we can denote that as G dash of S. That is the cascade combination of D of S into G of S, which is 1 plus KDS into 1000 root 2 by S into S plus 10 square. Okay, whole square. So we need to find the KD value. The given is phase margin equal to 45 degree and then omega GC equal to 10 radian per second. So omega GC is given. So we can replace S by j omega. So G dash of j omega equal to 1 plus KD j omega into 1000 root 2 by j omega into j omega plus 10 whole square. 10 whole square. Okay. Now, what is the relationship between phase margin and gain crossover frequency? So we know phase margin equal to 180 degree plus angle of j omega GC. That is phase angle at gain crossover frequency. Phase angle at gain crossover frequency. So from this transfer function, we can find the phase angle at gain crossover frequency. So angle of G of j omega PC equal to, so from the numerator, tan inverse KD omega KD by 1 minus tan inverse omega by 0 minus, and this is whole square, so 2 tan inverse omega by 10. Okay. So we can replace omega GC. What is omega GC value given? 10 radian per second. So tan inverse 10 kd, and this is tan inverse infinity is minus 90 degree. So if we replace omega by 10 radian per second, 10 by 10, 2 tan inverse of 1, 2 into 45 degree minus 90 degree. Okay, 10 kd. kd minus 90 minus 90. Okay, so phase margin is given as 45 degree now. So 45 minus 180, it will become 135 degree minus 135 degree. And here minus 180 degree plus tan inverse 10 kd. Okay, so if we simplify that, tan inverse kd will become tan inverse 10 kd. Tan inverse 10 kd will become 45 degree. Therefore, kd is equal to, kd value is equal to 1 by 10, which is 0.1. So this is the answer for this problem. 0.1 is the answer. Okay. So let me move to the next problem. The next problem is taken from the topic again Routh array only. And here transfer function is given k into s minus 1 g of s. So g of s is given 1 by s plus 1 into s plus 2. So we need to find the characteristic polynomial from this. So k s minus 1 by s plus 1 into s plus 2 is g of, you can mark it as g dash of s. This is open loop transfer function. So if we find the closed loop transfer function and then characteristic polynomial means 1 plus g dash of s. So 1 plus okay. So if we simplify this, s square plus 3s plus 2 plus ks minus k equal to 0. So that will be simplified as s square plus 3 plus k into s plus constant term is 2 minus k. So if we form the Routh array for this characteristic polynomial, this is characteristic polynomial. So if we form the Routh array 1, 2 minus k for the first row element, and s power 1 row element is 3 plus k, and s power 0 element is again 2 minus k. So for the system to be stable, the first column of the element should be positive. Okay, should be positive. That should be greater than 0. So for that, if 2 minus k greater than 0 means k should be less than 2. Okay, if 3 plus k, this is one conclusion. And if 3 plus k greater than 0 means k should be greater than minus 3. So that means for the stability condition, the k should lie between minus 3 to 2. Okay. Okay. If k is between minus 3 and 2, the system will be stable. So this is the range of k for stability condition. So let me check with the options. The first option is stable for all k greater than 2. No, for k greater than 2, it is not stable. So option A is wrong. Unstable for all k greater than 2. Yes, absolutely. Option B is correct. It is unstable after 2. So option B is correct only. Okay. And this is the last question. So the topic is root locus only. So this is one of the MSQ questions. MSQ, multiple select question. Okay. So here, the open loop transfer function is given. For k greater than or equal to 0, which of the following real axis points is or are on the root locus? So multiple options may be correct. So we have to check with each option. Okay. So from the given open loop transfer function, we can mark out the poles and zeros first. And we can locate the root locus first. See here, we can mark out the poles and zeros in the S plane. S equal to 0. What are the poles? What are the zeros? S equal to 0 and S equal to -2. So these are zeros. And then poles are S equal to -5, S equal to -7. So we can mark zeros are 0 and -2. And then poles are -5 and -7. So here 0, 2, -5, -2, -7. Okay. Now we check with the odd number criteria to locate the root locus. Okay. We can then only we can find out the real in which real axis point root locus lie. So between 0 and -2, we can choose one test point. We can choose one test point. We can choose one test point between 0 and -2. If we look at the right side, only one root, that is S equal to 0. So definitely we can conclude between 0 and -2, the root locus will fall. So we can mark out that, we can locate that as root locus. Okay. And then if we choose the test point between -2 and -5, if we look at the right side, there will be two roots. It is even. So we can eliminate that. We can conclude that there will be no root locus lie on these points. Okay. So if we choose the test point between -5 and -7, and if we look at the right side, there is three roots. So definitely there is an odd number. So using that, we can conclude that between -5 and -7, the root locus lie on that real axis points. So we can mark out that between -5 and -7. So if we choose any test point after -7, there will be four roots which are even. So there will be no root locus. So now root locus real axis points between 0 and -2 and -5 and -7. So let me check with the options. Option A is -1. It is lying between 0 and -2. So option A is correct. Let me check with the option B. It is -4. -4 is lying between -2 and -5. So it is wrong. So option C, -6 is lying between -5 and -7. So option C is also correct. Option D is incorrect. So A and C are correct. This is one of the MSQ question. In this, -1 and -6 are the correct values in which the root locus lie. This is Mani's Gate Tech Vision. We have solved gate problems. So this is a channel for engineering lectures. You can subscribe the channel. Thank you very much for watching the video. This is my mail ID, dmoneylecture@gmail.com. You can mail me. Thank you very much for watching the video.